Friends, so I hope you are all safe, keeping yourself isolated even after this Janta curfew yesterday. And so university has also decided that 50% of the employees will work on alternate days. So today is my work from home day. So I think it is better to utilize this by preparing this lecture. So let us discuss the last result of this section, which is Weierstrass Factorization Theorem. I hope you have got the links to the two previous videos. So let us recall what we have seen just quickly, uh, which we'll be using in this lecture. So definition of elementary functions, elementary factor we have uh, given, which is denoted by EPZ. For p equals to 0, it is nothing but E0z is 1 minus z. And for all others p greater than equals to 1, it is 1 minus z exponential of z plus z square by 2 plus up to z power p by p. And these are all entire functions, and EPZ has only one zero, which is at z equals to 1. So if we consider, instead of z, if we consider z by a, then EPZ by a has a simple 0 of order 1. So that is z equals to a, and it has no other 0, so non-vanishing elsewhere. And we have seen the lemma, this bound on mod of 1 minus EPZ, which was used in this theorem, which we have seen last time. So let us just understand the meaning of this result, which we have already seen last time. Uh, an is a sequence uh, such that mod an equals to tends to infinity. An is non-zero for all n greater than equals to 1. So this is a sequence in which the number of repetitions of this terms an is allowed a maximum finite number of times. So no complex number in the sequence is repeated infinitely many times. And if Pn is a sequence of integers such that this series is convergent for all r greater than 0, then this product converges in HC. We denote this by Fz. So Fz equals to product n equals to 1 to infinity Epn z by an. And moreover, this function f and this product have the same number of zeros. So this has zeros at an. So f also has 0 at all ans. And so this theorem gives function construction of a function with prescribed zeros given a sequence of complex numbers. What is a function that has the same number of zeros as that in the sequence? And so this is the only condition which is required for that. And what is a guarantee that such a condition will be satisfied? That is, what is a guarantee that such a sequence Pn exists? So there is one such easy example, that if we take Pn equals to n minus 1, then this condition is clearly satisfied. So it is possible to have a sequence. This theorem says that it is possible to have a sequence of integers for which this condition is satisfied. Therefore, it is possible to construct a function given a sequence an. It is possible to construct a function like this whose zeros are only an and no other zeros. So this is the meaning of the result, which we'll be using in proving Weierstrass factorization theorem. So let us uh, go through the statement first. Weierstrass factorization theorem. So suppose f is an entire function, and let an be the non-zero zeros of f repeated according to multiplicity. So don't get confused by this non-zero zeros. What does this mean? F is an entire function and an is a sequence of zeros of f. So f of an is 0, but no an is 0. An are non-zero complex numbers at which f is 0. And suppose f has a 0 at z equals to 0 of order m greater than equals to 0. So at z equals to 0, suppose f has a 0 of order m greater than equals to 0. Now we know 0 of order m greater than 0, but what about equals to 0? So 0 of order m equals to 0 at z equals to 0 means f of 0 is non-zero. If m equals to 0, that means actually f does not have a 0 at z equals to 0. So f is non-zero at 0. If it is greater than 0, then only it has a 0 of order m at z equals to 0. Is it clear? So f may not have a 0 at z equals to 0. Then m equals to 0. If m is strictly greater than 0, any positive integer, then f has a 0 of order m at z equals to 0. Yes, so what we are given? We are given a sequence of zeros of f. In this sequence, no term is 0, and 0 is also z equals to 0 is a 0 of f or of order m greater than equals to 0. If it is greater than 0, then it has order m. If it is equals to 0, then f has no 0 at z equals to 0. So this is the given. Then such functions are classified. They are of this form. Then there is an entire function g and a sequence of integer pn such that fz is of this form. Because it has a 0 at z equals to 0 of order m, we have z power m. If it has no 0, then m equals to 0. So this factor will not be there. Z power m will be 1 if it has no 0. And e raised to gz, such an entire function g exists, and product n equals to 1 to infinity e pn z by an, just like in previous theorem. So any function with given sequence of zeros, non-zero zeros, and z equals to 0 is a 0 of order m. So it is of this form, z power m e raised to gz for some entire function g and product of all these elementary factors. Right, so let us see the proof now. I hope the result is, statement is clear. So here we consider the finite case. So first we consider the sequence has only finitely many terms. So f has only finitely many zeros. In some books, they have not considered this case at all because they have given one condition, limit a n tends to infinity. So no zero, so this sequence is uh, diverging to infinity, limit mod a n tends to infinity. That means the sequence itself is infinite. But here we are not given any such condition. So although it is not given in the Conway, this case, but we shall consider this case. So suppose f has only finitely many zeros, counted according to multiplicities, and that are a1, a2 up to an. So f of a1 is 0, f of a2 is 0, f of an is 0, and all these are non-zero complex numbers. And also z equals to 0 is a 0 of f of order m greater than equals to 0. So z equals to 0 is a 0 of f of order m greater than equals to 0, and all these are also complex numbers where f is 0, but these are non-zero complex numbers. So suppose these are the only zeros of f. So because f is an entire function, we recall if these are zeros, there is another function from C to C which is analytic. So there is another entire function. Because z equals to 0 is a 0 of order m, so we have z power m. a1 is a 0, so we can take that factor also out. Z minus a1, z minus a2 up to z minus an, and hz, where hz is non-zero for all z in C. So this we have seen earlier in unit 1 itself. If f has a 0, then if these are the zeros of f, then we can take these factors out, and then there is another function hz, which is analytic from the domain of f, so C to C. So h is also an entire function, and hz is not 0 for all z in C. So fz is of this form. So then what we do is we take all these constants outside common, a1 up to an, so the product, and this will give us z by a1 minus 1, z by a2 minus 1 up to z by an minus 1, and hz. And then we write this product, but 1 minus z by ak, product k equals to 1 to n, all these factors we write 1 minus, so we have a minus 1 power n outside because these are n terms. Take minus outside, so it will have 1 minus z by a1, this will become 1 minus z by an, product of this, so minus 1 power n, a1 up to an, hz, and z power m as it is. So where hz is non-zero for all z in C. So now we'll focus on this term, minus 1 power n, a1 up to n, hz. If hz is non-zero, then this is also non-zero because this is just constant, minus 1 power n, and a1 up to n, these are just complex numbers which are also non-zero, and hz is non-zero. So this whole term is an entire function because h is entire function, all this is non-zero constant. So this whole term is again an entire function which is non-zero. So we use this corollary which we have already seen uh, in, if you remember, in the section of simply connected region. So G is simply connected, and f from G to C is an analytic function which is non-vanishing on G. Fz is non-zero for any z in G. Then we have proved that there is an analytic function from G to C such that fz equals to exponential of gz. So we are going to use this. So because as we have discussed, hz is non-zero, these are all non-zero constants. So this is also a non-vanishing entire function. Entire function means its domain is C. So C to C, this function is analytic, non-vanishing, and because the domain is simply connected, that is the condition here. So C is simply connected by the above corollary, this stated corollary. There is an entire function G such that this function is nothing but exponential of Gz for all Z in C. So what we do is we replace this part in the previous step by exponential of Gz. So we have Fz equals to Z power m exponential of Gz, product of all this finitely many terms, 1 minus Z by AK. But this is nothing but Z power m e raised to Gz, and product of, we know the definition, E0Z is 1 minus Z. So 1 minus Z by AK, that is nothing but E0 of Z by AK. So in the finite case, we have K equals to 1 to N. So this product is finite, but F has the required form, which was given in the statement of the Weierstrass Factorization Theorem. So in the finite case, we are done. Right? I hope it is clear and I am not too fast. So now we consider the infinite case. So the general case, assume that there are infinitely many non-zero zeros of f, an. So that means that is a sequence an is infinite. So now what is the sequence an? This an is a sequence of zeros of f. So f of an is 0 for all n. At each point an, f is 0, and all ans are non-zero, and the sequence is now infinite. We have already done the finite case. Now we assume that the sequence is infinite. And suppose z0 is a 0 of f of order m greater than equals to 0. If z0 is actually a 0 of f, then the order is m strictly greater than 0. If z0 is z equals to 0 is not a 0, then order maybe, I mean, it is m equals to 0, so it is not actually a 0. Then we note that because this is an infinite sequence, limit an equals to infinity. So limit mod an equals to infinity. We are going to use the previous result. Why this is the case? Because the set of zeros of f is nothing but an, and this is a countable. It's a sequence, so it is countable. So it is clear that f is not identically 0. Because if f is identically 0, 0 function has 0 everywhere. On every complex number it is 0. So we don't have a countable sequence of zeros. So f is clearly not 0, because the only zeros of f are this. 0 function has 0 everywhere, and it is not a countable set. So one thing is clear, f is non-zero. Now if this is not possible, so suppose if limit mod an is not infinity, then that means there is some m such that mod an is less than equals to m for all n, which means that an is a bounded sequence of complex numbers. So by Bolzano-Weierstrass property, every bounded sequence has convergent subsequence. So an has convergent subsequence. That means limit, let us call that subsequence as an suffix j. So that limit exists. But if the sequence of zeros has a limit point, then by identity theorem, if you recall this result, if the set of zeros has a limit point in the domain of f, then f is identically 0. So then, because an has convergent subsequence and an are zeros of f, so zeros of f has a limit point, by identity theorem f is identically 0, which is contradiction, because f is identically 0. These are not the zeros, only zeros of f. F is 0 everywhere, so this cannot be a countable set. So hence we must have this limit mod an equals to infinity. That means mod an tends to infinity as n tends to infinity. So now limit mod an tends to infinity, that, and these are the sequence. So we can use the previous theorem. Just read the statement if you have the notes with you. So there is a sequence Pn. There is at least one sequence we know, Pn equals to n minus 1. So there is a sequence Pn of integers such that this product z power m and product of ep and z by an, this product is convergent. Let us call it hz, and it has same number of zeros as f with same number of multiplicity by this result. Just read the statement of this result. And what is the guarantee that this sequence such exists? That is Pn equals to n minus 1. There is one such example. So this product is convergent in HC, and we let us call it HZ. So H and F have the same number of zeros and with same multiplicities. So because of this, Fz upon Hz has removable singularity at z equals to 0, a1, a2, and so on. See, what are the singularities of this function Fz upon Hz? It will have singularity when h is 0, denominator is 0. H is 0 where f is also 0. So those zeros will cancel out, and those are these points. Z equals to 0. This may or may not be. It depends where m is 0 or m is strictly greater than 0. A1, A2, and so on. So because they cancel out, so they are the removable singularities. And so f upon h is an entire function which has no zeros, because zeros of this are same. So f has no more zeros. So this f upon h is an entire function which with no zeros. Again, we use this corollary. C, the domain is simply connected, entire function. So f upon z non-zero, simply connected by this corollary. There is an entire function g, so that fz upon gz is nothing but exponential of gz. So therefore fz is nothing but hz into e raised to gz, and hz we just put the value of hz from the previous slide. So that is z power m, product of this epn z by an. So this shows that in the general case, even if f has infinitely many zeros, and the sequence of zeros is non-zero zeros is infinite, f has this form, which proves Weierstrass factorization theorem. I hope this is clear, and this completes this section. Thank you.